Hello, this is John Fitzmaurice, and I'm going to describe the simplified um, mathematical model for gas turbine speed control that I built. I used Bill Rowan's paper from 1992, his ASME paper from 1992, and I'm only going to do it at full speed, right? And as you can see, I'm going to cut out a lot of stuff. Everything in red I'm going to cut out. So starting at this summing junction, I included that summing junction. I have some set points that change. I took a PNID. I used a PNID instead of his transfer function. I used constants from a frame 5 that had a Woodward controller that uses PID control, and it worked just fine. Very stable. Responds to load rejection and things like that very well. I didn't put in these fuel limits yet, although I plan on doing it. Note 5 is the delay. I think that you have on a digital controller when you go in and out of the system. Now, notice I read it out, this X. Well, how can I just randomly decide to throw stuff out? Well, note it comes back here to N, which is speed. So as I explained in the previous video, all the you can't call them values, what do you want to call them? The phenomena like speed, turbine torque, gas turbine output, gas turbine valve positions are just 0 to 1. So 1 is full and are rated, and 0 is 0. So at rated speed, at full speed, N is equal to 1. And I only want to use this at N equal to 1. So at N, I don't have to multiply by 1 because you end up with the same number. And you end up, I also took it out here, rotor speed, on the turbine speed calculation, because if I multiply by 1 here and divide by 1 here, I haven't actually done anything. So this simulator only works around full speed. But in fact, speed control is only used near full speed. So we don't have to multiply and divide by 1 at various places in the, unless I really want to use this for part speed or to see how I would deviate, down to 90% or something. So anyway, that's why I took those out. So I included the gas fuel system, the delay of the turbine torque calculation. Then I summed it. This load torque was included, even if I read it out. This is the value for rotor inertia, and what they're saying here is it's actually a slope. If you take that transfer function, it's just you're going to multiply times tau 1 is what it means. Tau 1 is 17. Rotor inertia is given as they find it by taking the acceleration of the turbine. If you do a full load rejection, right, the speed will increase, especially in the first half a second or so, because it's getting full load before the governor responds and the valves close. So you take that first slope and you extrapolate it out to 200% speed. So you have 100% increase in speed. And from an Indian grad student paper I found on the internet, that value is 17. And the Indian grad student has a bunch of values for frame 5s, 6s, and 7s. Very interesting paper. And then that speed comes back here to the summing junction. So there we are. Next, I'll open up my simulator and give it a drive.